So Voltaic cells, the last topic that we're going to cover in the redox unit, it's really an application of the activity series content. So the overview of what a Voltaic cell is, sometimes it's called a galvanic cell. It's the second type of electrochemical cell besides electrolysis. The overview is that a Voltaic cell uses a spontaneous chemical reaction to produce electricity. Net, that means we're going to take chemical energy and convert it to electrical energy. This is essentially the explanation of how a battery works. So Voltaic cells are sort of simplistic precursors to our modern batteries. If you think back to our activity series, the activity series allows us to predict which combinations of metals and ions will react together spontaneously. Well, if we take those spontaneous reactions and we arrange the reactants correctly, we can allow this same spontaneous reaction to happen, but we set it up in a way that produces electricity. So if we think back, this is the example used in the activity series video and note session. So we've got copper metal and silver ions. This is a combination of reactants that will spontaneously react and produce silver metal and copper 2+ ions. So it's a spontaneous reaction. Now you can set up a Voltaic cell from the exact same reactants. So the things that are going to end up reacting are the copper and the silver solution, the silver ions. And the products are going to be a copper solution and silver. So what I've done here is I've created what we call two half cells to create my Voltaic cell. So on the left, I have a piece of copper metal, an electrode of copper, in a solution of copper 2+ ions, represented by this sort of square, which is my beaker full of blue copper 2+ solution. On the right, I have a silver half cell. So it's a silver electrode sitting in a solution of silver plus ions. So we know that the combination of reactants that should react is going to be the copper metal and the silver ions. Okay, but what we've arranged thus far, we would refer to as half cells. So no, I have two half cells, and so two half cells together is going to make the whole Voltaic cell, and each half cell is going to be where half of the reaction takes place, where the two half reactions take place. So the other pieces that you need for a Voltaic cell are you need wires, just like you needed in the electrolytic cell. So there are external wires. The external wires, in this case, instead of attaching to a power supply, because a power supply would provide electricity, in a Voltaic cell, we're going to create the electricity. And the way that we show that we're measuring that electricity, usually the simplest way is to draw a box with a V in it. That implies that you're showing a voltmeter. So you got to have half cells for your Voltaic cells, and you have to have a voltmeter. Okay, so that's how we show it, just a box with a V in it. Okay. So this will show us the electricity that we're producing, the voltage, and the wire allows the electrons to transfer. We're going to need one more thing. We need to complete our circuit when we make a Voltaic cell. And the way that we complete the circuit is with something that we call the salt bridge. And I will explain what that does and how it works a little bit later on in the video. But for now, I'm just going to draw it and I'm going to label it. All right. Okay, so the idea is the copper and the Ag+ react spontaneously together. If I put them right next to each other, the electrons will trade right along the surface of the copper. The copper will dissolve and the silver will plate onto the piece of copper. And so I'll end up with all this sort of mossy silver being formed. Well, what happens in the Voltaic cell is really the same overall reaction. The copper is going to dissolve into copper 2+ ions, and the Ag+ is going to form silver. But they don't actually ever get to physically touch each other. So the way that it happens is that electrons, which from the half equation we can see electrons are leaving copper and going to Ag+. So what's happening is that the electrons, in order to do that, they actually have to travel through the wire. This is my attempt to draw little arrows. Okay, so the electrons leave the copper metal. They get pulled off the copper metal through the external wire, through the voltmeter, down the silver electrode, and down to here, where the Ag plus ions can now get them. So that same transfer of electrons, the transfer of electrons from copper to Ag plus is going to take place. That same pull of the electrons off of the copper to the Ag plus is going to happen, but in doing so, it's going to pull the electrons through the external circuit, and that's what creates the electricity. So the electrons spontaneously want to go from copper metal to Ag plus ions, and in order to do so, they're going to travel through the external wire. Okay? Notice that's just like the electrolytic cell, that electrons travel in the external circuit. Okay, well, what's happening on the internal circuit? Well, one over here, you have Ag plus, and it's moving towards these free electrons, and when it gets them, it's going to turn into Ag solid. So just like in the previous activity series video, the net reaction for silver is that the ions are going to get reduced. They're going to gain electrons, and they're going to turn into Ag solid. That's the half equation that's taking place over here. Well, on this side, when the copper gives up those electrons, it gives away 2 electrons, it ends up forming copper. Give me a sec. Ends up forming copper ions. Okay, and so it dissolves apart, gives away 2 electrons, and turns into these copper 2 plus ions. So same exact half equations that occurred in just the regular spontaneous reaction are also going to occur here. If I want to balance them, then clearly right now the electrons are not balanced, so I need 2 Ag pluses, 2 electrons to make 2 silvers. Okay? So what you can see is that the 2 different half equations that are taking place actually in a voltaic cell occur in 2 different half cells. They occur actually in separate locations. So over on the right-hand side, you have the silver half equation, and over on the left-hand side, we have the copper half equation. Now, if we think back to how we're going to label these electrodes, first off, we can do anode and cathode. The copper reaction, the copper is losing electrons, and so that means this is the oxidation half equation. And I know that from my mnemonic, N-ox goes together. So the copper electrode is going to be the anode. Well, if I go to the silver electrode, clearly the come on, my computer's being a little slow, and there we go. Okay, so this is the reduction half equation, and so red cat, that tells me that the silver electrode is the cathode. All right, the other thing I'm going to do is try to label it as negative and positive. If we remember von Poe, now we're going to be using von for the first time. And von tells me that in a voltaic cell, oxidation happens at the negative electrode. So I've already identified that over here, the copper electrode, this is where oxidation is happening. So the copper electrode is the anode, but it's also the negative electrode. And that makes the silver electrode the positive electrode. So this is a reversal of the electrolysis, which I know is going to frustrate many of you. But what determines whether or not it's positive or negative has to do with the direction of electrons. What happens with anode cathode has to do with oxidation versus reduction. And because a voltaic cell is really the opposite thing from electrolysis, it's a spontaneous reaction producing electricity, in some ways it makes sense that the electrodes have a reversed signage. So that you're just going to have to deal with it, and the mnemonics can be a helpful way to try to remind you. So copper is negative, silver electrode is positive, and one other mnemonic that we didn't get to before is called fat cat, and it says that it's referring to how do the electrons flow in either one of these cells. The electrons always flow from the anode to the cathode. Okay, so the copper is the anode because the electrons leave the copper and they travel through the wire and they get to the cathode, which is the silver, that way. So it tells you how the electrons move in the external circuit. So in the end, we have this voltaic cell. We have our two half equations. We can figure out which is oxidation reduction, which helps us figure out anode cathode, and it helps us figure out negative positive. The overall equation is just when I balance the electrons and add them together. And the last thing to deal with is what's the role of the salt bridge. The salt bridge is just it can be something soaked in a saltwater solution, or it can be a saltwater solution inside of a glass tube, a U-shaped tube. But essentially, the function of the salt bridge, one simple way to say it is that it completes the circuit, which it does electrically. It allows the movement of ions between solutions, and this keeps the half cells electrically balanced, so balanced for overall charge. Common things that are in salt bridges are potassium chloride or potassium nitrate are the two that the IB tends to use. All that happens in the salt bridge, if you imagine in the first scenario, as the electrons are falling into the silver cell, that would very quickly lead to a negative charge buildup in this cell, which would then repel any more electrons from coming into it. And that's kind of a problem. So what happens instead is that as the electrons flow into the cell, whatever the positive ion is in the salt bridge will also naturally flow into this cell. So if we have positive ions in here, they will naturally flow into this cell as the electrons flow in, and that will help keep it overall neutral. On the other end, as the copper is losing electrons, a positive charge would build up over here. So the salt bridge has negative ions in it, and the negative ions are naturally going to flow into this cell to keep it electrically neutral. So the salt bridge just provides ion movement and keeps the overall charge neutral. Over time, you would see observations like the copper would be getting smaller, it would be dissolving and losing mass, and over time the silver would be getting plated onto, would be getting bigger and would be gaining mass. The copper solution would be getting darker and darker blue in this case as more and more copper ions enter it. The silver ions, you wouldn't see a change because silver is a clear ion. It's a colorless ion. And lastly, how is charge conducted in this voltaic cell? Just like the electrolytic cell, in the external wire, you have electrons that are conducting the electricity. In the internal electrolyte portion of the cell, you have ions that are moving. You have the copper 2+ ions, which are falling away from the electrode, and you have the silver plus ions, which are moving towards the electrodes. And then you have ions in the salt bridge, which are moving into both cells. So inside, it's always ions, and external is always electrons. Right? And so we can use, make sure we know all these different mnemonics. We can talk about half cells, voltmeter, external wires, internal electrolytes, salt bridge. We labeled the electrodes. Final things to go over. You're going to see things about voltage and current. Those aren't too important for you guys in SL, so I'll leave them off for now. Cell diagram convention is, I think, a rather minor point, but we'll go over it just because it's here on the video, and then we'll stop. For this voltaic cell that's made of a copper half cell and a silver half cell, the cell convention would be to write copper, because that's the thing on the left, backslash copper 2+. So that pretty much describes one half cell. Try to make my plus sign. I would draw two vertical lines here that represent the salt bridge. And then on the other side, I would draw the other ion, right? Because the salt bridge sticks into the two solutions. So the two solutions, the two ions, should be on either side of the salt bridge. And then I would have AG. So I don't think it's going to be a major issue, but if they talk about the cell convention, it's just a way of describing a voltaic cell in sort of shorthand. And so I've got one half cell over here, one half cell over here, and the salt bridge by these two vertical lines between them. And that is voltaic cells in a nutshell, and we'll talk about it more in class.